Okay, off we go. So, welcome everybody. Thanks for coming. Last day of class before fall break. And in advance, I hope everybody has a good fall break. Don't forget about the attendance quiz, attendance code, all that jazz. Back into the math. So, we were talking last time. Let me just, super quick call back. We looked at two different ways to slice up this domain, and I'm going to say we learned a lesson. Right? So, same question, right? And you can choose between, either of these two different ways to compute, and, pretty clearly this one's better, and this one's, we don't want to do that one because it's got square roots to be fair, in the bounds, but they're the inner bounds, which means they're in the outer integrand. Right? So, highly undesirable, probably depends on F, blah, blah, blah. But all else being equal, who wants square roots, right? So, the moral of the story was, think about what you would like to solve for in terms of what, and then choose accordingly. I would much rather solve for Y. And I've arranged to solve for Y by putting dy on the inside. Right, that's a nice, simple way to think about it. Right, if you make the poor choice, I think it would be a poor choice of putting x integral on the inside. Then you're going to have to solve for x, and you're going to get undesirable stuff. Okay, all right. So, moral of the story. Moving along, let's go learn another lesson. So we're going to learn this next lesson by, again, considering the same question twice. We're going to slice it two different ways, see what happens, and then we're going to decide which one we like better, and then we're going to try to figure out how to sort of anticipate this in advance so we can hopefully just avoid the problem in the first place. So here is our question. And let's see. Let's be real quick about this. We've done slicing several times now. I think y'all are probably good with the procedure. Going in this order, y goes from 0 to 1, right? And then for a given value of y, x is going to do like this, and it goes from this value that comes from this point that's on that curve, for which I can solve for x and get that. And then it ends this value, which comes from that point, which is on that curve, for which I can solve for x, and I get that. Okay, so that's the slicing process. We get this integral. I don't see anything particularly wrong with that. Cool, let's call that plan A. Plan B, let's slice it the other way, see what happens. And at a casual glance, if you look at the domain and you think, all right, if I'm going to do my x slicing first, well, doesn't x go from 0 to 2? You'd be tempted to write that down. Here's the problem. For some values of x, right, when x is between 0 and 1 in particular, for those values of x, let's just try to, let's go look a little ways down the road and try to see what's about to happen. Let's look at the upper bound for y. The upper bound for y is going to come from this point, which is on that curve, in which I can solve for y and I get this. But if I look at x between 1 and 2, if I look at the next range of values for x, the larger values of x, there, my upper bound for y comes from this point. It's not on the red curve. Now it's on that purple curve, which has a different equation, which when you then solve for y gives you a different upper bound for y. So this is why we can't write the integral down in the first place as being from 0 to 2. If I say single iterated integral, I'm going to let x go from 0 to 2, which one of these formulas would I use? Well, you kind of have to use both of them, right? That's a problem, right? And so we kind of have, in order to make the inner bounds possible to write down in the first place, I have to break up the outer bounds into two separate intervals. Did you see what happened there? It's really undesirable. Right? So we're going to have to compute double the integrals, literally twice as many iterated integrals. That's double the work. Okay, so obvious preference, right? We'd like to do half the work, not double the work. Okay, so now again, let's try to anticipate, right? How do you see this coming in advance? And there's different ways to say this, and I'm just going to show you the way I think is the most easy to sort of see coming. Roughly speaking, the problem is that the upper bound points that had been on that curve kind of jumped over to this curve. That's really the problem, ultimately. Right, the points that I used to find the upper inner bounds jump between two curves. Why did they jump between two curves? Well, because those two curves intersected, right? It's only because they intersected that it was even possible for that to happen. What else do we notice? Thinking out loud, rhetorically, when two curves intersect, and I'm going to say it creates a corner. Generically, all exceptions granted, but think corner. So here's my streamlined strategy, and that is, as you are looking at how to slice, for example, if I'm doing my dx slicing on the inside, as I'm doing like this, as I'm doing my x slices, try not to slice right through a corner. Nice and pithy. Just try not to slice through a corner. Every time you slice through a corner, pretty much, I mean, let's think broad strokes. When you slice through a corner, you're going to have to stop whatever integral it is that you were working on, start a whole new integral, right? Because those inner bounds are going to be different. So trying to slice through a corner. Now let's look at the first way that we did it, and notice that actually is fine and dandy. Here I was slicing. Let's do this in green because it's all going to be good. We're doing dy on the outside. There's the y direction. Here's what our y slices look like. And notice nowhere in the process do I slice through a corner. I mean, I guess technically I sliced through a corner at the very beginning. Yeah, cool. I wasn't doing an integral already that I need to stop. I was going to start a new integral there anyway. That's fine, right? You can start at a corner. And now, to be fair, I also end by slicing at a corner. I was done anyway. I have no new integral to start. Right? So start and stopping at corners, yeah, fine. But in the middle of your process, notice not slicing through any corners. How are we doing? Does everybody see the little moral there? Okay. All right, so I think this is a very convenient rule to keep in mind. So you've got kind of two rules. These are not, set in stone. All exceptions granted, right? But try to think about which variable you'd like to solve for and which variable you would very much prefer not to solve for. And then try not to slice through corners. And good news, usually these rules, when they both suggest, when they both suggest a choice, they usually suggest the same choice. There's probably some counterexamples out there, but anyway. Sometimes, though, and in fact, I would say fairly often, notice with this first problem, there's no corner issues in either direction. But the which variable do you want to solve for gives strong guidance. Here, the corner issue is the one that makes the important choice. But which variable do you want to solve for? Whatever, who cares? They're all pretty much the same. So it's good to keep both of these ideas in mind. How we doing? Everybody's happy? Okay, here's another example. There's two cool things about this example that I like. So let's just dive in. I'll point out. Well, let me not get ahead of myself. So we've got two surfaces. We've got this paraboloid, And we've got this plane. And notice that there is a volume in between, right? So this is sort of what I've got in gray here that I'm highlighting in purple. There's that volume that's sandwiched in between, that's sort of contained in between those two surfaces. And the question is to find what is that volume that's in between. Okay. No domain given. Now, this happens sometimes. It's pretty natural. And so how are we going to figure out what the domain is? Well, first of all, I have to decide how am I going to slice this up. And as I slice this thing up, effectively, what is the two-dimensional region I would like to think of as being sliced up along with it that I can then call the domain? Okay. So I'm going to slice, if you will, vertically in both directions. Right? Again, like just imagine that this is like a cup of French fries, right? And so we're going to slice it like that. We're slicing it like this, making a bunch of slices that look like that. Is that cool? And notice, while I do that, every one of these slices has what I'm going to call a shadow down here in the XY plane. And so as I slice up the solid in question, I'm also effectively slicing up the shadow. And I can therefore think of it as that I have the domain is this shadow. And for every little piece of the domain, keep in mind, and by the way, let me go back to, here's our first glimpse at a two-index Riemann sum, aka double integral. The big idea is that if we have a two-dimensional domain, chop up the little two-dimensional domain to pieces, just like we've just done. And the idea is that an integral is where you're adding up a bunch of pieces, and each piece is something times the area of that piece. Something, for whatever reason, always different, depends on the application, something times the area of that piece of the domain. So going back to our problem, some students get sort of uncomfortable with, wait a minute, this volume. I thought double integrals compute volume under a graph, but isn't that volume supposed to go all the way down to the XY plane? No, don't. That's not the right way to think about double integrals. Don't think of double integrals as volume under the graph. Again, it's one of these sort of occasionally relevant, but usually not. Features of a double integral. A double integral, as we just discussed, you should think of as any sort of summation where you got something times the area of the piece of the domain. And notice that's exactly what we have here. Here it is. If I look at the volume of this little French fry, it is literally something times the area of the piece of the domain, because that area of the piece of the domain is the same as the area of the base of this little weird shape. And what am I multiplying by that area? Well, it's that height, and that height is just the difference of the two z's, so it's z2 minus z1. Does that make sense to everybody? Everybody happy with that? Okay. I think it's a really important point of view. Can't emphasize this enough. Much better to think of double integrals as something for whatever reason appropriate to whatever it is that you're computing. Always going to be different. Always think about the application. But something times the area of whatever piece of the domain you're looking at. Yeah.
Is Z2 referring to the plane?
Whichever one is on top. So let's see here. The top point, that top point is on the plane, and so Z2 is this Z2 right there. Yeah. Yep. We'll get into the algebra in a second. Okay. Alrighty. So here's the other interesting part of the problem. So we've taken a question that came to us, no domain given. We've identified, let me rephrase that. We have reconceived of the question as now being something being added up over a domain, right? So we tailored a domain for our purposes. Now we have the question, how do I find what that domain is? It's still kind of, I can talk about it. It's the shadow, there it is in the picture, but it's not described algebraically yet. So that observation, how you figure out what that domain actually is, or how to write that domain algebraically, I argue as follows. Okay. Let's see here. Okay, well, first of all, I'll point out, in the domain, you can talk about the height up to the paraboloid. That's this value of z. And at that same point in the domain, you can talk about the height up to the plane. That's that value of z. And of course, their difference, z2 minus a z1 gives you the height in question, and we've already talked about that. I'm going to make the case, geometric appeal, right? You got to see it from the picture. The points that make up the boundary of our domain, I propose, are the points where the height up to the paraboloid and the height up to the plane are the same. What do you think? Anybody buys it? Geometric appeal. You got to kind of see it from the picture. Let me say it this way: the shadow down here, the edge of the shadow comes from this kind of edge of the shape. By the way, every shape is different. Right? Not all shapes have this feature. Right? So in this case, though, very conveniently, the edge of the domain is the edge of our shape. This edge is literally where the surfaces intersect, and where the surfaces intersect, the two z's are the same. Okay. All right, so that's the instructions on how to find that boundary, which is what we really needed anyway. And so as I write here, we're going to take that z, which, by the way, x squared plus y squared, I'm going to require that it equal to this z, which, by the way, I have to do a little bit of algebra to solve for it in terms of x and y. I get this. And so our domain, so the boundary of our domain, this curve that we need, is described by when those two z's, the green z and the blue z, are equal. Happy? Everybody's good? Let me give you a landmine notice. Let me show you what students do wrong on this a lot. Pretty commonly, easy mistake to make if you're a little too casual and careless about things. Some students make the observation that, well, I need to understand this curve. This curve is where the two surfaces intersect. And then the following sentence sounds reasonable until you think about it and realize it's nonsense. I want the surfaces to intersect, so I want the equations to be equal. You see the temptation. I'm just going to point out that is absolute nonsense. When two equations are both satisfied, that does not mean that both sides of both equations are all equal. It just doesn't. 7 equals 7. 3 equals 3. Those are both true, even when 7 does not equal 3. Right? So anyway, make sure to see that distinction. I mean, the actual carried through mistake that I see a lot, and again, it just doesn't make any sense at all, is I'll see students setting this equal to this. And I'm like, why? That doesn't make a lick of sense. Right? There's no geometric motivation for that at all. It's just kind of, I don't know, it seems like it's a good sort of wild guess, I suppose, but again, a little analysis doesn't make any sense at all. How are we doing I want to make sure everyone knows not to step on this landmine. Everybody comfortable with that? All right. Okay, and then I guess the last thing I'll point out, this has come up previously, and here it is again. Every so often, you need to be able to complete a square. so that you can recognize an equation that you have, which is like, oh my gosh, what is that? It's hard to tell what that is. You can turn that into something you can immediately recognize as being a circle. And, details, where's the center, what's the radius, blah, blah. But anyway, that's the algebra defining the domain. Okay, moving along. We are done with 5.2. 5.3 is super quick. Take a look, right? I'm not going to say everything that's in all of 5.3, but the main topic is changing the order of integration, and this is just, we're going to do one example, and I think you'll catch the strategy, and it's just a matter of doing it. So here's the question we're going to ask. How would I compute this integral right here? Already written as an iterated integral. Isn't that nice? So it seems like it's just a matter of plug and chug. The problem is, the very first thing we would have to do is compute the inside integral. Computing that inside integral, I would need to take an antiderivative of e to the x squared dx. I don't know if y'all are aware of this one, if you remember this one, but that doesn't have what we call a closed form antiderivative. You can't write its antiderivative in terms of, like exponentials and polynomials and stuff like that. It just doesn't work. So, oh my gosh, right? We're in trouble. Everybody see the problem, right? The very first thing that we need to do to be able to compute this in the usual way, we can't. All right, so here's the little clever trick when things like this happen. And by the way, sometimes with different motivations, work backwards. Take the iterated integral, pull it back to reinterpreting it as a double integral, and slice the other. So let's do that. This is pretty much just undoing what we always do. We're going to look at where y equals 0. And where y equals 1, it basically says right there that's going to be our range of values for y. Y is going to go from 0 to 1. Right? And let's see here. I guess I'm going to have to, I hope that's still legible. Y'all read that in the back still? Okay. All right, so from y equals 0 to y equals 1, there's y equals 0. There's y equals 1. And then notice our inside bounds, x starts at y. So here's the line x equals y. And then it ends where x equals 1. And boom, there's our domain. Nothing to it. Everybody see the process? And we're just kind of undoing the slicing process that we did. I'll say it. We're undoing the slicing process that we would have done to turn the double integral over this into this iterated integral. All right, and now it's all over but the shouting. Believe it or not, this is going to work out great. We take this domain, right? We reverse engineered our domain. We slice it in the other order. And let's see here, x goes from 0 to 1. And then for any given value of x, y goes from 0 to x. Right? Details, make sure to think that through. And that gives us this integral, and at a casual glance, you're like, yeah, that e to the x squared is still in there, and oh my god. Right? But here, this inside integral now is a dy integral. That means that x is literally a constant for the purposes of that dy integral. That means I treat x as a constant. That means this whole integrand is a constant. And so the dy integral is actually pretty easy. Right? 0 to x gives you that factor of x. Now we have to face up to the scary integral. This is, trying to deal with this exponential now with x as a variable, and this, we couldn't the analog of this previously we just couldn't do. But because we did the dy integral first, we have this extra factor of x That makes a U substitution available, and poof, we're done. It's a very clever idea. Everybody happy with that? Every so often that'll come up. Okay, so that's section 5.3. Read the rest of it, but that's pretty much the idea. Okay, on to 5.4, triple integrals. I'm going to say, sometimes we need to chop up not a one-dimensional interval. Oh, let me switch to highlighter mode. Not a one-dimensional interval, thus giving us a one-index Riemann sum, aka a single variable integral. Not a two-dimensional domain, giving us a two-index Riemann sum, aka a double integral. Sometimes we're chopping up not a one-dimensional domain, not a two-dimensional domain. Sometimes we're chopping up a three-dimensional domain. Stands to reason, right? Reasonable extension. We're just extending our previous extension. Why would we ever want to do such a thing? Well, frankly, because we live in the three-dimensional world, right? I have a lot of stuff that's three-dimensional, right? Maybe this fish tank, right? Just an easy example. And maybe I want to count maybe there's little pieces of pollution floating around in my fish tank, and I want to add up all the pollution. And what I'm going to do is break up and look at each little piece of the water of the fish tank, one at a time. On each little piece, I'll talk about pollution per unit volume to be multiplied by volume, and then add up over all of those little pieces of volume. I mean, it's totally the same idea, right? We're just going to try to extend that three-dimensionally now. And there's a couple of details to keep track of, but the big picture strategy, just what I said, on each little piece, appropriate to the whatever it is we're interested in. Give me 2 seconds. Of whatever the application may be, stuff per unit volume, typically, times volume, gives us stuff. And then we add up over the whole to get the grand total amount of stuff. Yes?
You'll get this in a sec, but what specifically are we measuring here?
Yeah, that's the beautiful thing about it, is that it could be anything. Right? So it's just like when you go back to here. I mean, people like to see an actual thing that they can look at and point to, right? And that's satisfying, and it ties your hands, right? If you decide, I'm going to interpret, and this is kind of why I don't like the area under the curve interpretation here. If you decide that integrals are area under the curve, okay, well, you just tied your hands and now you're stuck, right? So if we keep this vague, this could be anything. I don't know what f is going to be. It depends on the example. If I'm computing mass, this is mass per unit length, etc. Keep it vague, keep it ambiguous, then it could be anything.
But I'm just saying, like, what differentiates this from, if you go back down to the next slide?
Talking about here?
Yeah. Uh-huh. Like, is this essentially just doing, like, a double integral of, like, the first one minus, you know what I mean? Can you just do the top minus the bottom?
No. Absolutely not. No, because there might be more pollution down at the bottom of the tank and less pollution at the top of the tank, right? Very importantly, whatever your integrand is, whatever your density is, whatever your concentration is, whatever it is that you're multiplying by volumes, could be a function that varies all over the tank. Does that make sense?
Yes.
Yeah. So this is not a situation where a double integral will do. Absolutely not. There are some rare examples, highly coincidental, very fortunate examples where in some amazing stroke of good luck, maybe there is no dependence on z, perhaps. And that does change things a little bit, but even then, I think it's kind of unnatural to try to argue it as a double integral. Yeah. It's a great question. Absolutely. Okay, how are we doing so far? Everybody kind of see, I mean, there's details to be written down, etc., but do you see the sort of, this is analogous to the two previous versions of integrals we've talked about? All right, so yes, our strategy, again, don't know what we're going to be computing, but if it's something that accumulates, if the whole is the sum of the parts, then I can look one piece at a time, and if on each single little, not a sub-interval, not a sub-rectangle, it's a sub-box, maybe, right? Something like that. If on each such little piece, what I'm interested in can be written as something times volume. Typically, quantity per unit volume times volume. Then this is the perfect tool to represent our strategy for computing. And as such, it deserves a name and a notation, and you can probably guess all of this. We're going to call it a triple integral, because we're going over a three-dimensional domain. We're going to use three integral symbols. The size that we're multiplying by, it's no longer length, it's no longer area, now it's volume. So we're going to call it dV. And I think this notation is pretty believable. And by the way, notice again, I'm just making a subscript indicate the entire domain. And how we actually do the computations, and are we going to have an iterated integral here? Yeah, we'll get to that. We'll have to, include, but there's much more to say about how do we write down the domain in an iterated integral. But for the purposes of a triple integral, just make sure it's well defined and make it a subscript. Okay. All right. So again, now I'm sorry. Did I hear a question? No. Okay. We are real quick going to observe. I've already kind of talked through this example, but if you've got a three-dimensional region and you have mass distributed throughout that three-dimensional region, I would argue first, mass is an accumulating quantity. The whole is the sum of the parts. Very important. Can't just go around assuming that. Not everything has that feature. There's different kinds of things that you're going to be interested in computing that do not do that. So always make sure to think that through. Make sure your quantity in question actually adds up the way it's supposed to. And then on each little piece, mass is mass per unit volume given times volume. Okay. All right, now we'll get to computations in a second. I want to give another warning. I think you can get yourself into real trouble with the following. Let's think about single variable integrals again. This is how everybody was taught single variable integrals, right? It's area under a curve. All high school calculus classes, most high school calculus classes like to present it this way. It's kind of satisfying. You can see it. Satisfying. Y'all will recall, of course, I encourage this point of view. Again, I make the case how often it is that you actually, in fact, need to compute area. Not as a means to an end, but as an end in itself. That area is the goal of what you want to compute. Yeah, usually not. So I think this is weirdly specific and constraining, right? So I like thinking of it as stuff per unit length times length, and mass has this nice feature that it's a kind of a stuff that's visceral and relatable, right? We all have experience with mass, right? And so I think it's got that advantage, and it doesn't sort of pigeonhole us like area does. Okay. All right. And now recall as well, you can talk about analogous pictures for double integrals. You could, I suppose, think of volume under a graph surface as how to think of a double integral. Again, I've been pushing, I will always be pushing this point of view. No, think of it as you're adding stuff up over an area, right? That could be any stuff, but we're accumulating over an area. Okay. What about triple integrals? You might be able to see this coming. Right? Single variable integral, two-dimensional picture. Double integral, three-dimensional picture. Well, if you want to have an analogous point of view, you're going to have to try to figure out how to interpret triple integrals as a four-dimensional picture, let me rephrase that, you are out of luck because you can't visualize a four-dimensional picture. Right? Everybody on board? So this is another reason, I couldn't really explain this reason at the time, but this is another reason not to like the area point of view on single variable integrals. It sets up a pattern that is unsustainable. I suppose all patterns are unsustainable. If we had a quadruple integral, both of these are dead in the water, right? But at least we can get a little further with this other point of view. This other point of view makes perfect sense for triple integrals. And you really can have a single point of view on how to understand integrals that applies just as well for single, double, and triple integrals. You just have to view it this way as accumulation of stuff and forget about graphs and area volume question mark. It's just not a good plan. How are we doing? Does everybody see the problem? By the way, here's another thing I should just point out. Again, I've seen it a million times. Certain number of students like to think of single variable integrals this way and double integrals this way and triple integrals this way for lack of better option. And now they have a consistency problem, right? And this can lead to sort of like, well, wait a minute, they're both volumes. I mean, why is one a double and one's a triple? And you can see how there'd be a lot of potential confusion there. So I think that's a really bad idea. And make sure not to fall into that trap. Does everybody see my warning there? All right. So now that said, I want to be realistic about this. While these are the points of view that I encourage you to make your cornerstone points of view on all three of these kinds of integrals, I recognize there are some pretty nice features of thinking of single variable integrals this way. So that's fine, but I'd prefer that this be secondary. I would encourage you to make this in your mind secondary. And likewise, there are situations where this is useful too as a backup, depending on the situation, can be useful kind of point of view as well. As secondary points of view and with the big asterisk that it doesn't work here. Okay. Good news, bad news. The bad news is this point of view on double integrals was a tool that I used to provide y'all some sort of intuition for why double integrals and iterated integrals compute the same thing. And computationally, you can always turn a double integral into a iterated integral. I used literally the volume under the graph example as my tool for trying to make that intuitive. Well, if I were going to do that for triple integrals, I would have to do it with something I can't draw. So I'm not going to be able to give you that intuition for why is it that triple integrals can be computed with triple iterated integrals. And I'll just say two things about it. For one thing, just because I can't visualize the picture doesn't mean there isn't a picture. It's just a picture that's inaccessible to us mere three-dimensional humans. Right? Secondly, that's for intuition purposes anyway. There is a much more rigorous and mathematically robust take that does not require any picture at all, a purely algebraic take. It is subtle, it is sophisticated, it is riddled with landmines that you have to worry about. It's not appropriate for this class, so I'm not going to go through it. But the good news is it works out, and it's fine. So, moving along, I'm just going to make this claim that, yep, if you have some application written as a triple integral, yes, indeed, you can compute that triple integral with an iterated integral. And in fact, furthermore, how you order your differentials, now you have 6 options, by the way, right? 3 things can be ordered in 6 different ways, not just 2. All 6 of them will give you the same answer. So you got lots and lots of options, which again, kind of a double-edged sword. Okay. And again, we're going to come up with the same sort of 3-step process. This is our kind of roadmap. You'll recognize this looks just like the double integral roadmap, right? It's just that we don't have this is the 4-dimensional notion that we can't make sense out of, and therefore we can't make sense out of these. But again, the only purpose for that anyway was so that we could make this connection that I'm claiming, asking you to trust me. Okay. So our 3-step process. 1, whatever your application is, write it as a triple integral. 2, rewrite that as an iterated integral. 3, plug and chug. Cool. Let's do one. Let's compute the amount of mass in this region. I argue first that mass is an accumulating quantity and mass is density times volume. So I rewrite the mass question as a triple integral. Each little piece of mass is the corresponding little piece of volume times mass per unit volume. Adding up over the whole domain. Yeah, everybody all right? Second, we assert, with appreciation of the theorem above, that triple integrals are computed with triple iterated integrals. By the way, notice that the range of values for y came from literally the range of values for y on our domain. And the range of values for x comes literally from the range of values of x for our domain, etc. For z, range of values for z. Cool.
Any reason you're doing it in that particular order?
Yeah, 6 options, take your pick. In the case of what I've got here, it very much does not matter.
Okay.
Yeah. I mean, the computation will look a little different, but it's equally inconvenient or convenient both ways.
Gotcha.
Yeah. And then plug and chug. Now, we got to be careful. Remember, we do have a rule that says when you're looking at an inside integral, the variable further to the outside is constant. Well, now we have 2 variables further to the outside. I'm going to draw a picture to motivate this in a minute. But variables further to the outside, we're going to treat as constants. I claim that they are literally constants. So this xy right there, constant. And because for this inside integral, z is our variable, that 2z, the antiderivative is z squared. Let's see, let me get that bigger. Everybody see what happened there? Okay. Reminder, it's part of the job of the practitioner, whoever is working out, you in other words. When you're working out a triple integral, right, you have to keep track at which stage of the calculation is which variable behaving in which way. And so for the z integral, x is treated as a constant, as is y. Once we get to the x integral, x is no longer a constant, x will be the variable, etc., etc. So make sure to be careful about that, as always. Okay. All right. So, how's this slicing process work for non-rectangular domains? Oh, yeah, question.
Sorry, for the integral, z is still considered a constant, though, even though we already did in the next time.
You mean for the x integral?
Yeah.
There is no z. It's all integrated out.
Oh, because, okay.
Yeah. Is that cool?
Yeah.
Good deal. Okay, yeah. So non-rectangular domains. Let me remind you, going back to here, back to when we were doing double integrals for non-rectangular domains. It's pretty much the same. Not that much changes. The only thing it changes is that the inner bounds are going to be functions of the outer variable, right? We talked that through. And furthermore, thank the maker, we don't have to draw the n plus 1 dimensional picture, right? For a double integral, you don't need the 3-dimensional picture. All you need to do is look at the domain, right? And so in particular, the outside bounds are just sort of top to bottom. And then for any given value of the outside variable, you look at that corresponding slice of the domain. And only on that corresponding slice are we interested in the range of values of the next variable, in this case x. Right? So when we look for the inner bounds, it starts here because that's where the slice starts. Right? And it ends here because that's where that slice ends. We determine these by looking at just the y slice, one y slice at a time. Is that cool? Everybody remember? Okay. So it's the same game for for 3-dimensional, and I think the best way to do this is just to dive in and let's just do it. And I'm going to go ahead and expand this out. I think I'm done with callbacks. 3-dimensional lump, non-rectangular. By the way, I'm going to do this integral with dx on the outside. No particular reason. We're going to see many examples where we're going to make various different choices, but just to get the ball rolling, let's put dx on the outside. And what does x do? Well, way back here is the lowest value of x for our lumpy solid, and then way over here at the front is the greatest value of x on our lumpy solid. That's our x bounds. Cool? Then, as per usual, we fix a value of x. Oh, whoops. I wanted that green. We fix a value of x. We look only on that x slice. So I'm going to, oh gosh, and the art is hard on this. So, yeah, you got to use your imagination here to a certain degree. We're just going to look on the slice. I'm going to imagine that I'm cutting through this at that value of x. That's the x slice. And then I slice in the next direction. My next direction, apparently, let's see here, we have an x selected. Now I'm going to slice in the y direction. Now you do have to use a little bit of geometric imagination here. This is an unavoidably geometric subject. Unavoidably. Right? So there's no sort of algebraic work around here. And by the way, I'm fully aware that there's a lot of high school multi-teachers out there telling students that there's an algebraic workaround. No, there's not. I have a counterexample that will put that to rest. You have to see it from the picture. You have to look and see what are you actually writing down. On this slice, when I start looking at a range of values for y, right, y is going to have a first value. This is the lowest value of y on our x slice. And then there is going to be a greatest value of y on our x slice. Again, looking only at the x slice. That's how the process works. Now we're going to fix a value of y. Here's where you're going to have to use your imagination a little bit. When we fix a value of y, keep in mind we've already fixed a value of x. We're already committed to only looking at this x slice. Now we have to further commit to looking only at that value of y's y slice of our x slice. Use your geometric imagination. I claim that for that value of y, we're going to get just kind of a line segment there. What do you think? Everybody see that geometrically? Okay, so let me redraw the picture then. Fixing now both x and y, namely looking above this point right there only. That now is the remaining slice of the domain, x and y both fixed, for which I need to know about z. And z is going to have a lower bound, and z is going to have an upper bound, and those are going to be your inner bounds. Everybody happy? Everybody see kind of how this slicing process works? It's heavily geometric. Right, by the way, we'll go out on the following observation. We're not going to be able to get to an example today, but look how much I relied on my picture. And this was a made-up, non-specific picture. In real examples that we're going to be working on, the details of the shape will matter, and your picture needs to be good enough to allow you to work and not only deduce what the right features of your shape are, but also good enough to communicate your analysis of what you're doing. Right? So you are going to need to be able to produce reasonably good pictures. If you need practice with three-dimensional drawing, take a look at the videos I have on that on my Miscellaneous Topics playlist. It's everything I know about 3D drawing. Hope you'll find that useful. Y'all have a great break. See you on Wednesday. Okay.